Hello. Today's video, we are going to be introducing the topic of equilibrium. So we will be talking about the definition of equilibrium and also our different types of equilibrium. Now, at equilibrium, we will see that we have the rate of the forward reaction being equal to the rate of the reverse reaction. And we'll talk more about that in a second. But in order for a reaction to reach equilibrium, it must be a reaction that is reversible. So it's got to be able to proceed in either direction in order for it to be able to come to equilibrium. All right, so if we have a simplistic reaction like A plus B turns into AB, so that would be the forward rate. And then the reverse reaction would be AB breaking apart into single A and single B. When we are at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So every time I make one AB molecule, another AB molecule breaks apart. Therefore, that ends up keeping the concentrations of all of our substances constant. So not necessarily equal, they will be constant. So the rates are equal, and that causes the amounts to stay constant. Now we will talk in later videos about if we change any of the conditions, we change the concentration, gas, if we have a gas, the pressure, temperature, that may alter the equilibrium, but we'll talk more about that in later videos. So our main idea is this definition that the rate of the forward is equal to the rate of the reverse, which then causes the amount of everything to remain constant. We have three different types of equilibrium, and we'll talk about them on the next slides: phase, solution, and chemical. All right, so in phase equilibrium, this exists between two different phases. So it's simply a phase change, so a physical change, not a chemical reaction. So for example, if we have a glass of ice water. So if we have a glass of ice water, we have water, and then obviously we have some ice cubes. If this is at equilibrium, every time an ice cube melts, so if we lose an ice cube here, then we also have to have a new ice cube form. So therefore, we can see that the rate of our forward is equal to the rate of the reverse, and that the amounts of everything stays constant. So I'm keeping 3 ice cubes in there. So again, remember the amount on each side of the equation are not necessarily equal to each other. The amounts, the concentrations of everything stays constant. This example down here would be showing H2O liquid at equilibrium with H2O gas. So every time you get a molecule evaporating, a new molecule condenses. So you'd be keeping the same amount of water and the same amount of molecules in the gas phase. So this would occur at 100 degrees Celsius. This equilibrium between water and ice would occur at 0 degrees Celsius, assuming that we're at standard temperature, standard pressure. All right, our next type of equilibrium is solution equilibrium. So by definition, saturated solutions are at equilibrium. So if you remember from when we talked about solutions, if a solution is saturated, it contains the maximum amount of solute dissolved. So if we have a saturated solution of salt water, every time one solid particle dissolves, another one must recrystallize. So since the rate of dissolving forward reaction is equal to the rate of the recrystallization, that would be the reverse reaction, that makes our solution at equilibrium. So again, Saturated solutions are at equilibrium. If we have an unsaturated solution, we would just be doing the forward reaction, which would be dissolving. And if we have a supersaturated solution, then we would be doing the reverse reaction. Our third type of equilibrium that will cover the vast majority of the examples that we will look at is chemical equilibrium. So here we have chemical changes or chemical reactions occurring. And again, the concentration of all of your reactants and products remains constant if we're at equilibrium. So now we just have a quick example. So on this list, we want to classify them as phase, solution, or chemical equilibrium. So the way that I like to do it is I like to look for phase first. So phase has to be exactly the same thing on both sides of the arrow. The only thing that's changing is the phase. So there can't be any rearrangement of atoms, any bonds broken, any bonds formed. So we want to look down our list and look where we have the exact same thing on both sides of the arrow. The only thing that's changing is the phase. And that would be example number 5. Because we have C2H5OH, which is ethanol, as a liquid, and then it changes to a gas. But it's exactly the same molecule on both sides of the equation. There's no bonds broken, no bonds formed, no rearrangement of atoms. Our next one that I think is the second easiest to pick out is solution equilibrium. So here we will have an ionic substance dissolving into water and splitting apart into its ions. So that is shown in number 2. So we have NaNO3 ionizing into the sodium and the nitrate ions and forming an aqueous solution. So that would be solution. And then literally everything else will be chemical. So number 1 is chemical, 3, and 4. Now notice in 4 there is also a change of phase, but the more important thing is that there is the rearrangement of atoms, the changing of the bonding, which signifies that it's chemical.